All right, now time for another part of the final review series. This is going to be a review on acid and base chemistry. So identifying what is a good base, what is a bad base, what is a good acid, what is a bad acid. And also I think I threw in some examples of electrophilicity and nucleophilicity, as these are sort of related concepts. So first I'm just going to do a general overview to remind everyone sort of the factors at play. And then we'll go through actually quite a few different examples. And these are just examples from old tests, old problem sets. I tried to grab each one that I saw from either a practice exam, a real exam, or a problem set, just so that we can all have them kind of in one place. So if you want to go and do the problems on this slide deck first to kind of test it out and then go back and watch the video, that might be a more effective way to approach this. So probably the biggest strategy we have to determine the acidity or basicity of a molecule, particularly if we're trying to compare different molecules in a series, is to consider how stable is the conjugate acid or conjugate base. So here I have pyridine, and here we are adding a proton. The nitrogen would then be protonated, and that would be its conjugate acid. So we can see what type of factors might be stabilizing or destabilizing this nitrogen atom along the way. Conversely, if we wanted to go look at, say, the acidity of something like methyl acetate, now we're going to be taking away a proton, and this would lead us to an enolate. So in general, we're going to be looking to see if these conjugate acids or conjugate bases are very stable. If they are very stable, that means it's going to be a very good acid or base that you started with. If this molecule is highly unstable, it's very reactive, then we're going to say it's not very acidic or basic. So rarely do we talk about this in absolute terms, like because usually it's all relative and comparing different molecules in a set. So we're going to see which one has certain features versus ones that don't. So in order to start looking through the different types of options, one of the biggest elements would be, the type of atom that it is. And so electronegativity of the atom will be the major factor here, especially in the cases we look at. Sometimes the type of atom polarizability also comes into play. But for the most part, electronegativity will tell us a lot. So if you have an electronegative atom like an oxygen, usually this leads to making better types of acids because the oxygen atom is going to make a very stable conjugate base. It's good at stabilizing negative charge. And then the less electronegative atoms, say a nitrogen, would be a better base because if it gets protonated, it is able to manage that charge a lot better. So now if we're looking at, say, the same type of atom, they're all the same element in a series, we need to consider some other factors as well. Hybridization will be our next thing to consider. As we talked about in the previous video, things with more S character or atoms with more elements with more S character will be more electronegative. So an sp nitrogen will be much more electronegative than an sp3 nitrogen. That means that the sp3 nitrogen is going to be less electronegative, meaning it's a better base. And so conversely, if you're looking at S character of an acid, S character will be very good for the character of an acid because you have a lot of S character. It's going to be good at stabilizing the conjugate base. But if you have a lot of S character on a base, that means that the positive charge you need in the conjugate acid will not be well stabilized. Also remember, this is only useful when comparing charge on the same type of atom. So all of them are oxygens, all of them are nitrogens, or all of them are carbons. If you're trying to compare an sp2 oxygen to an sp nitrogen, this becomes a much more challenging comparison, and I probably wouldn't give you that situation to look at unless we had a good reference point or is involving one of the pKs that we definitely know to use in that context. The other thing to look at is resonance. If you're able to generate a resonance stabilized conjugate acid or conjugate base, that probably means that it's going to be more acidic or more basic in its original form, because this tells us that the conjugate acid or base will be quite stable. If you're losing resonance upon protonation or deprotonation, this is going to be a negative factor. This is going to be something that hurts the acidity or basicity of a compound. So if we look at the deprotonation of, say, methyl acetate, it used to have this really nice resonance interaction with the neighboring carbonyl, and now we don't have that interaction anymore. We still have this lone pair, but now you see it's unable to put its electrons into that carbonyl, and this means that it lost some of its stability. And this is the reason why esters are less acidic than something like a ketone that didn't have that starting resonance stabilization. Aromaticity we can view as a special case of resonance, and that means that it'll be its effect will be magnified relative to normal resonance effects viewed in similar cases. So this is our pKa tables in the next 2 slides. I would say it wouldn't hurt to go back and kind of look at some of these different examples. I mean, we could go back and look at the ones we're supposed to already kind of have known as reference points. And I think you'll see that a lot of the elements, or if you look at comparing different molecules in these series, this will start to make sense now. So if we look at the conjugate acid of, say, acetone versus a carboxylic acid, now we can explain this 1 pKa difference because the conjugate acid of a carboxylic acid does have resonance stabilization where we can put that charge on 2 different heteroatoms, whereas we do not have the same benefit with the acetone case. And so I think and a lot of these you can start to maybe use this as a case to be like, can I figure out why 2 similar molecules have slightly different pKa's just by using some of these first principle examples. And also to remind that things we should know are hydronium, acetic acid's around 5, or any other carboxylic acid. The ammonium ion, and this is referring to the NH4+, this is around 9. A phenol is around 10. Diethyl or dimethylmalonate. This is actually a little wrong because it says diethyl here and there's methyls drawn. But for either one, this would be around 13. And you can note that dimethylmalonate is 13, whereas the corresponding diketone is 9. So we see the impact of that ester coming into play already. We have water at 14. Alcohols are slightly less acidic at 16, and that's because the carbons, the alkyl substituents are slight electron donors, destabilizing that alkoxide. We have acetone around 19 or 20. We have a terminal alkyne at 25, and we have ammonia here at 36. And the idea of using all of these is each of these will help us to understand cases where we can't directly use reason to explain what the relative magnitudes are, and at times this is very useful. So you don't necessarily need to know exactly what the pKa of disopropylamine is. We can probably say, to a good approximation, it's about the same as just ammonia. So let's do some practice problems and see where we go. So this first question is, which of the following compounds is the weakest base? And I even say, consider the stability of the conjugate acid. So one thing to note is that in all of these examples, they all feature nitrogens. So now we don't have some sort of element difference. We're not comparing an oxygen to a nitrogen or anything like that. So the next thing we probably want to look at will be the hybridization. So we can go list the hybridization of these nitrogen atoms. In a pyrimidine, this is going to be sp2. Triethylene is hybridized as sp3. You can know that A is sp2 because it has double bonds on the nitrogen. C is one of those cases where we are going to have an sp2 nitrogen because this is going to have aromaticity. So this lone pair is actually involved in the pi system, so it will stay as a purely p orbital, and that's how it is able to gain aromaticity. We have acetonitrile, which is sp, and E, we have this amidine in which both nitrogens are sp2. Again, this lone pair on this nitrogen will be in a p orbital, so it can be in conjugation with the imine carbon-nitrogen bond. So already we're able to determine actually the weakest base of all of these just from this first hybridization analysis. Sp hybridized nitrogens will be the most electronegative. Electronegative atoms will be very poor at stabilizing the conjugate base. So the positive charge in this nitrogen will be very angry. And since it's very angry, this is a very unstable conjugate acid. It leads the nitrile to be the least basic of all. The next question is one on 2-aminoimidazole. So this is a case where we're trying to figure out where is the most basic nitrogen on the molecule. And we're given a number of different options. So once again, we're all using the same different nitrogens in the molecule. All these nitrogens are sp2 hybridized initially, though they can change their hybridization state a bit upon protonation. Along the way, all of these are involved in either in resonance of some sort, except this lone pair out to the side. This lone pair is outside the plane of the pi system. This lone pair is in the plane of the pi system to make it aromatic. And the lone pair on this NH2 to the side is donating into the ring and will also have some resonance contribution. When we go and look at all the different options, we can see that A and C, they both lost aromaticity. So this is one of the cases where we kind of need to consider what was the state of the molecule before the resulting conjugate acid. So loss of aromaticity is going to be pretty bad. And so unless all the other options are even worse, this is something we definitely want to probably think of as being not the site of protonation. If we look at B, it is still aromatic. So maybe this won't be too bad. We have the NH, we have the positive charge on a nitrogen. This nitrogen went from sp2 with resonance to sp3 without resonance. So this did take a penalty along the way. So while it is an sp3 hybrid, the loss of resonance actually counts a bit more against that nitrogen overall. And it won't be as basic as your normal type of tertiary amine, because the aminoimidazole itself has an sp2 carbon that will be more electronegative than your normal alkyl substituent. If we look at E, it's not as obvious, but this also lost aromaticity. Whenever the lone pair is used to make a bond, it no longer can be used in the pi system. D is our last option. Note that we still have aromaticity. Because we still have this lone pair able to interact. We still have a lone pair on this nitrogen atom as well. So this is actually able to go and further stabilize this anion, even though this resonance structure technically loses aromaticity along the way. It'll still help to contribute to the overall stability of the conjugate acid. So this ends up being our best choice. It's because we didn't lose any resonance stabilization or aromaticity upon protonation, whereas in each of the other cases we do have this penalty emerge. So this is a fairly complicated scenario, probably a bit harder than what I would put on an exam, but I think it highlights a lot of these elements of where not only do we consider what is the stability of the conjugate acid, sometimes we need to take into account what type of resonance was lost along the way. So here we have a case where we're just looking for what is the weakest acid. Again, I think a good way to approach this is we can see that we have oxygen atoms all around. So oxygen, oxygen, 2 oxygens here, oxygen, and an oxygen. One way to look at this is, okay, we should know some pKa's for each of these. This is about 16, this is about 10, this is about 5. This is also going to be about 10, but it'll probably be a little bit higher than B because this methyl is slightly donating. So we don't really need to think too hard between B and D because we already know that A is a weaker acid than both of them. And the last one we have is E. We don't have any ether pKa's memorized, but at the same time, there's not a hydrogen on the oxygen. That means no matter where we deprotonate, we're going to have to break some sort of CH bond. And this CH bond would give a conjugate base that would be a carbanion. This is going to be very unstabilized because we're not able to put it on the electronegative atom. We don't have any resonance stabilization. If anything, we actually have some charge repulsion from the neighboring oxygen because we have two filled orbitals that might be interacting with each other. And so the closest analog we have for something like E would be probably your other types of just normal hydrocarbons that end up being, more than 45. So this one relies on a bit of maybe intuition or knowledge of carbon being actually it's going to end up being an anion on a different type of element, more so than trying to really compare all the different types of oxygens from first principles. So E will definitely be the weakest acid. We just talked about this in the previous video, but again, we can go back to sort of our reference points of the carboxylic acid is 5, the alcohol is 16, the alkyne is 25, and this is some sort of hydrocarbon, so this is definitely going to be above 45, if not closer to 60. So this will allow us to quickly establish the relative order, and when thinking about these types of problems, having some of these reference points in mind will quickly allow you to solve them, instead of having to go and think a bit more deeply about different types of stabilizations of conjugate acids or bases. Here we have a series of phenols. So our base point for phenol is about 10. And so we're going to assume that we're going to take into account different sort of substituent effects to figure out which one probably has the lowest pKa. The one with the lowest pKa means it'll be the most acidic. And so what we're trying to do now is further stabilize the conjugate base. That's going to further stabilize a phenolate. So things that will stabilize a phenolate will be things that are able to be strong electron withdrawing groups. So this helps us to quickly eliminate something like D, where we have electron donating groups on the ring. We have things like C, B, and C, where we have chloride. So these are electronegative substituents. They probably will lower the pKa a bit through inductive effects, but it'll probably be not as strong as something like a nitro group. So we end up having two different nitro groups that we're going to be really trying to compare in this analysis. So I'll draw each one out because the position of the nitro group does end up playing an important role here. So from an inductive effect perspective, the nitro group in the meta position actually probably has slightly stronger inductive effects. Inductive effects go through sigma bonds. So the one that is just closer in terms of bonds to the anion will have the greatest effect. But resonance effects will always override these types of small inductive effect differences. And the key relationship we have here is that we can actually push electrons from the phenolate all the way down into the pi system of the nitro group. So because of this stabilizing resonance interaction, this is going to greatly increase or decrease the pKa of the para-nitrophenol. So now we have an analysis of the conjugate bases. The one with the most stable conjugate base will tell us what is the strongest acid or the molecule with the lowest pKa overall. Now we have a similar type of analysis. Which of these alcohols is expected to be the most acidic? So we're looking for the same thing, the phrase change from lowest pKa to most acidic. And already we see that we have a nitro group again, and it's in a para position. So this is very tempting to just jump on this answer and be like, oh, this still must be the same one. But now we have something else at play. Note that we lost all the double bonds. So now instead of pKa of about 10 for any of these, plus or minus depending on substituents, now we are actually going from a pKa of 16. And this nitro group no longer is able to stabilize by resonance, so actually a cyclohexanol should be quickly eliminated. It is 6 orders of magnitude from its starting point, and it's going to be very difficult to overcome this with just some substituent effects through induction. So then we're going to still use the same rationale as before. We still want to stabilize the phenolate conjugate base. To do that, we need electron withdrawing groups. The NH2 is a strong electron donating group, so that doesn't look good. The methoxy is also a strong electron donating group, not quite as strong as the amine. The chloride is electronegative, so this will have some inductive effects. So this will be mildly electron withdrawing. Remember how the halide would slow down the rates of electrophilic aromatic substitution. And then we have A with this methyl, which is a mild electron donating group. So it's probably not that B is way more acidic than the rest, but we can come to the conclusion that it will be the most acidic of the series. Whereas each of these other examples will probably will be a higher pKa than phenol and less acidic. B will be a little bit lower pKa and more acidic. Now we have an electrophilicity question. So again, the rules slightly change. Rather than looking at conjugate acids or conjugate bases, sometimes we want to imagine what is the resulting product if a nucleophile were to attack the electrophile. How does that change the stability of that next step? And this becomes instructive. So just through a cursory examination, if we're trying to look at, and we can also couple this to which one should be the most reactive overall from its ground state. If we look at something like B, enamines are actually nucleophiles, not electrophiles, so these actually won't really react with nucleophiles at all. We can get rid of that. We have D and E, which end up being neutral compounds versus their analogs C and A, which are positively charged. We'd expect positive charged molecules to also be much more electrophilic. They want electrons. And now it comes down to an element difference. We have a nitrogen versus an oxygen. Oxygen is more electronegative, so that means that its starting charged compound, this oxocarbenium, is going to be more reactive and less stabilized than an aminium where nitrogen has the charge. This lets us make the decision of A. Trying to determine the same relative electrophilicity of something like D and E can also be done. We can also imagine that this oxygen is much more polarized than this carbon-nitrogen bond. It'll put more partial positive charge on this carbon. So again, a ketone is more electrophilic than an imine. Imines actually are really poor nucleophiles on their own. They need to be protonated or alkylated in order to get a reaction to take place at its carbon. That's because if we were to try to have a nucleophile directly add in, we end up with this highly reactive amide that we know acts as a wicked strong base and tends to be highly reactive.